but it's a little twist. It's a little, I don't think most of you will be that bothered by it. I would, because as I said before, you guys are smarter than me. So here we are, the unit circle, and you already know what a unit circle is. It's just, it has a center, go around it. Radius is always 1, okay? That's the unit circle. We're going to talk about, they call them circular functions because we're on the circle. We're actually talking about the arcs that are being moved as you open an angle from here to here. That's an arc. So it becomes a circle if you do all the arcs. We're going to look at values of circular functions. It's very complicated why they make these words. I never used to make it that complicated. Find values of lengths of lines. And I probably won't be doing this. I'll probably skip that part. Linear speed and angular speed, we'll take a stab at it. It's been a while since I looked at it. We'll take a stab. Vocabulary, you know what a unit circle is. We take all the trig functions and we call them circular functions because they're on the unit circle. Reference arc related to the reference angles that we've already done. It's just that when we have a reference, if I'm on a unit circle and I do a reference, we do a different color from that to that. This is my reference angle. This would be my reference arc. And if you knew geometry and you were measuring that arc as far as a degree measure, I believe, and I'm not really great at geometry, that angle theta is related to that arc. Did you guys get to circular geometry? And I think they're the same. But arc length also has measurements like miles, inches, centimeters. But it also can be a 30-degree segment, a 30-degree arc, because it's related to this 30-degree angle here. Linear speed, how fast are you going in a line from point A to point B, like miles per hour, inches per second? Well, think about running around a circle. If you're at a track meet and people are running around the track, isn't that track also measured like a 440? Those that ever ran track, a 440 would have been 1 time around, and an 880 was 2 times around. That stood for meters. So when you run, let's say you did a 440 1 time around. It's a good fast race, okay? And you finish that 440 meters in what's a good time? Probably, okay, let's say you did it in a minute. 440 meters per minute. Even though you were running around an arc, it still had linear speed. Now, if you know anything about running, you could run 440 meters here from A to B faster than 440 meters in a circle, because we end up something affecting you called the angle velocity. That when you're going in a circle, you can't run as fast as you can straight. It slows you down. So what happens is a good runner, they run super fast, then they get to the curve and they're not as fast. Super fast, and then super fast to the finish line. You know, that's how it works for anybody who has run. Here is how we're going to turn this thing into a circular function. Here's my reference. Well, this is really not my reference angle anymore because now I'm in quadrant 2. And typically, we always talk about the angle from here. And we still will. But here's my arc labeled S. And look what he's doing. He's kind of now talking about S instead of theta, or this theta. That's my reference theta. He's saying, well, in relationship to the circle. Now, can I think about what he's done here? Why is he saying x equals cosine of y? I mean, cosine of s. Why is he saying x is that? On that circle, no matter where your point is, like in this case, I'm x, it is some, this to me, erase what I wrote on it. So, not because you need it, probably more because I want a clean slate while I'm at it, is that the trig function is based on where you are on the circles. That also has a point, some x, and then obviously some y. As the point moves on the circle, the x and y's are changing. Look what happens if I just move up to here. My x is still 0, and my y now is a 1 because it's a unit circle. Look at that ordered pair. If I want to know what the sine of this point where I'm at right now, the sine of this arc, I'm going to call it S, will still be, okay, what if I say opposite over the radius, but the radius is 1. So it's opposite still. We also did sine of an angle, but I'm using the arc. And instead of using the opposite, I called it the y value. Remember? Because it's, when I looked at this two numbers, I always told you, this is my x, this is my y. Sine is always, if you look at what's happening here, and if I drop this down, well, I can't drop it down here. If I drop this down, my y is a 1, my r is still a 1. So I can talk about the sine value here at, you called it 90 degrees, but we've learned now it's not 90 degrees no more. It is 90, but we call it pi over 2, okay? So that's my measure in radians. But just look at this right here. How do I have two people sitting in there? Let's see. Okay, so go back to sine of some arc equals to y. Well, that's what I have right here, because it's a y over 1. And cosine of that same arc would be the x value. Since r is always a 1, you're always going to have, here's my x, here's my y. Here's my cosine, here's my sine. And I did stress that to you before. This is your cosine of theta. This is your sine of theta. It doesn't matter that we're talking in relationship to the arc. Cosine of the arc length versus sine of the arc length. It's the same thing. Here's my cosine answer. Here's my sine answer. Tangent was y over x, right? Y over x. So in this case, my tangent of pi over 2 is undefined because my x is a 0 and 1 over 0 is undefined. Now that I know that x equals cosine r or s and y is sine of s, remember what we said before about in that triangle here? If I just do a triangle and I call this x and I call this y, which is what's happening here, we know that because of Pythagorean theorem, x squared plus y squared equals radius. X squared plus y squared would have been the radius squared, which is 1. That's related to something we had before. And he's telling me right here, look at this. Remember? Well, he's telling me that, but I'm going to substitute. I think he does it somewhere. Where did he do it? He will in a minute. I guess I'll do it now. If x squared plus y squared becomes 1, And I know x is really a cosine, and y is really the sine. If I use my substitution, x squared plus y squared equals to 1, and x is really cosine of s squared plus sine of s squared equals to 1. Have you seen this identity before? It's going to be on your test.
No,
You haven't seen it before?
I don't think so.
We have.
Ooh, arm wrestling. You're in a fight. It's in there. It's called a Pythagorean identity. Remember, I made you do this. I bet you remember this, Secant. If I say divide everything by sine squared s, sine squared s, divide by sine squared s, it gives you the cosine over sine, which is cotangent squared s, plus sine squared s over sine squared was 1, equals to 1 over sine squared, which is cosecant squared. Remember this, Secant? When I did all three of them?
Yeah, sir. It's ringing a bell.
It's ringing a bell. Well, it's not like you've done it a lot, and it's not like you've done it for years. You just saw it. So at least you're honest. And most of you guys probably are in the same boat. You said, what? Okay. So we know sine of the arc length is y, and the cosine of the arc length is x. And we're only calling it the arc length because he's calling these circular functions. So picture s as theta. Replace s with theta, and it'll all mean the same. Tangent would be y over x, which I just explained it. Now take each of those and flip it. Y over 1 becomes 1 over y as long as y is not 0. X over 1 becomes 1 over x. That's your secant. And y over x becomes x over y. That's your cotangent. I love this picture. It's everything all rolled up into one. I don't know if that's the same picture I said I would make a picture of and blow it up. If it is, great. If it's not, then I want to use this one now. Because look what I can do here. As a matter of fact, I think in a couple problems I added a few of these pictures here. I'm going to use my familiar friend, 30 degrees, right here. And maybe we do it. I might be ahead of myself. So if I get to the section that's talking about this, if I drop my line to the perpendicular here to make that right angle, and obviously he's calling this S, and I'm calling this my theta. Something's very interesting is that because I dropped this down, made that 90 degrees, you may not be able to tell, but this X value is this X value. This X value is measured square root of 3 over 2. And the Y value is a 1/2. That's the triangle that it made. And now I bet you're wondering, well, where do those numbers come from? Well, it's a 30 degree, right? I purposely put it there for you. And I'm just going to remind you, because this is on your test. What is sine of 30 degrees, either by memory or by using some common sense right now? I'm going to do it. You're thinking. I know you're thinking. So I'm going to put my 30 degree here. That's a 1, 2, square root of 3 triangle.
1/2.
It is 1/2. There's the 1/2, because this is your sine. And the cosine of that same angle, cosine of that 30 degrees based on that triangle, is adjacent over hypotenuse, square root of 3 over 2. This is my cosine answer. And it just so happens on the unit circle, this height of this right triangle is 1/2. This length from the center of the circle to where I go up to that angle is the square root of 3 over 2. Sort of a miracle. okay? I don't want to beat a dead horse, so I'm going to draw another angle to my favorite angle in the world, 45 degrees or pi over 4. Now, obviously, we know that that angle here is 45 now. And based on our last few sections, a 45, 45, 90 is a 1, 1 square root of 2 triangle. Unfortunately, I'm on a unit circle. So things have to change because that distance still has to be a 1. So it has to still be a 1. So how can I change my sides to be related to that 1 here? And you look right here and you get square root of 2 over 2 and square root of 2 over 2. And you're probably wondering, well, how did that happen? Let me draw my 45, 45, 90 for a minute. 45, 45. 1, 1 square root of 2 is what I call it. Sine of 45 degrees or pi over 4 is opposite 1 over the hypotenuse square root of 2. And if I rationalize that, that becomes square root of 2 over 2, which is exactly what I have here. So the answers to what I believe to be true about a 45-degree angle is that ordered pair. This is not actually a 1 in this case. This is actually the square root of 2 over 2. This is square root of 2 over 2. They are the same. Since these are the same, then we know that it's a 45-degree angle. If these two legs are always the same, then they're always the same measurement. So this distance is not a 1. Let's see what that distance really actually is. Because I'm curious, how did it get a 1? Square root of 2 over 2 squared plus square root of 2 over 2 squared is 2 over 4 plus square root of 2 times square root of 2 is square root of 4. That's 2 over 4. That's 4 over 4. It is a 1. Wow. That only happened because instead of 1, 1 square root of 2, I had to make this distance square root of 2 over 2, square root of 2 over 2, and that's where it turns into the 1. So a lot of stuff you could do on this chart. If you could print one off, why don't you print yourself 10 of them? And then start trying to look at this thing and try to make some sense. We're still going to play with it a little more here because, oh, here it is. There's this chart first. This got kind of more, this chart was more work than I wanted to think about, to be totally honest with you. Symmetry, he's talking about symmetry. And frankly, I just want to survive. I don't really want to talk too much about symmetry. Oh, he has more notes up here. The unit circle is symmetric. Let's see, here's the circle. Here's the axis. Here's my x. Here's my y. Do you see symmetry on this picture? Is it symmetry to the x-axis? In other words, is the picture you see here the same as the picture you see down here?
Yes.
Okay, so I'm going to say the unit circle is symmetric with respect to the x-axis. Is this picture symmetric to the y-axis, the same side?
Yes.
The y-axis. Is there another form of symmetry?
Origin.
How do you know?
Because it's a unit circle.
So every point that I go here, I have a matching point on the other side of the origin, right? This point here matches up with this point here. So what happens if these points are 180 degrees? Or you can say this, if this was a spinner, and I put my spinner here, my pin, and I push the circle and rotate it 180 degrees, would the picture still be the same picture if that circle spun?
Yeah.
Yeah, that's rotation on the origin. So that meant it is and the origin. The point AB on the unit circle this is too much thinking. I don't know why they're making us do this, to be honest with you. But if a point AB lies in the unit circle, then, okay, that meant with symmetry to the x, that means negative A comma B will also be on the circle. That's flipping over the y-axis. Also, if I flip over the x-axis, then A negative B is also on it. Also, if this was AB right here, and I rotate it 180 degrees to be down here, what would that point now be? I think it's a negative A and a negative B. I think. Somebody can correct me. Negative A, negative B. So that AB, and I'll try to draw it here. If I flip it over the x-axis, the A stays there and the B becomes opposite. If I flip it over the y-axis, the A became negative, but the B stayed the same. If I rotate it 180 degrees, then they both become negative. Yeah, I think I'm right. Furthermore, each of these points has a I don't know what he wants. Furthermore, each of these points has a blank blank of equal magnitude. I don't know what he's talking about. I don't know what he wants there. Maybe it's in the book, but I don't know what. Off my head, I don't know what words he wants. Sorry. If you figure it out, hit me up with it. You can earn points, but I don't know what he wants. Back to here. Now we're talking about the unit circle. He wants to talk about the symmetry. And I think I put a copy of the circle here. This is not in your notes, so you might want to refer back to the other page. Okay? Because we're looking at pi over 3. So let me just draw that. Pi over 3. That's in my head. It's like when I speak English and Spanish. Sometimes I'm speaking Spanish, but I'm thinking English because Spanish was not my first language. So pi over 3 is a did I say pi over 3 or pi over 6? Pi over 3. That's 60 degrees in my head. Okay, that goes through here. Boom, 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 boom. Okay, wonderful. Look at that angle. Look at this angle. Look at it where it is up here on the circle. Okay, look at that point right here. Let's talk about the symmetry of that point. If I just have one to this point, this is not symmetrical to anything. It's just one point here. Okay, and so what quadrant am I in? Because he's got a word quadrant. That's 60 degrees. It's quadrant 1. Symmetry was no symmetry, none. And he wants to know about a corresponding point. Well, I'm going to cheat. I'm going to cheat because I have a chart. Even though I could do it. I could do the work. Okay, I won't cheat. I don't want you to call me a cheater. If that's a right angle, and I label that triangle here, okay, and this is always a 1 because it's on the unit circle. And I'm looking at the values he's got here. Now, can I develop those values without his help? Yes, I can, because I'm going to think 60 degrees, okay? I'm going to show you I don't have to cheat. I will cheat in a minute, but that means this is 90, and this has to be the 30. And this distance is a 1. And so this would be the opposite side of 30. So let me take it from the not a 1. Let me just leave that blank for a second. Like we did in the last chapter. I labeled it as 1, 2, square root of 3. Of course, that's not here because this is a 1 right here. But watch this. Watch this. When I call that a 1, I guess I can try to do it from here. If I cut this in half and call it a 1, these two triangles have to be proportional because this is still 60 and this is still 30, right? So if I cut the hypotenuse from 2 to a 1, then I have to cut these in half as well because it's proportional. So that this value now becomes a half. And this value has to become, what's half a square root of 3? Square root of 3 over 2? Yes or no? That good? That's the actual answer. Well, look at the ordered pair. 1/2 comma square root of 3 over 2. So I went to my 1, 2 square root of 3, and I said, well, what if this becomes a 1? This was an easy one because half of 2 is 1. So that just meant every number had to be cut in half. We could have done the same thing with that 45, 45, 91, but it was just a little more complicated. I should have done it that way. It's just hard because it would be a square root of, they had a square root of 2 over 2. Anyway, so I didn't have to cheat. So I know this is a half. I know this is the square root of 3 over 2, and that had to be the 1. So that's the ordered pair we're talking about. So I'm going to go to my chart, and I'm going to say the ordered pair was 1/2 comma square root of 3 over 2. Okay, now, do I have to cheat for the cosine? I don't have to cheat. Even if I ignore that circle, okay, and I just use this one here, what is the cosine of 60 degrees? Is adjacent over hypotenuse. So from this picture, adjacent is the 1, and the hypotenuse is a 2. Go figure. The cosine is a half. And what is the sine of 60 degrees? Just on this picture here from like last week. That is opposite over the hypotenuse. And what do I see? Opposite square root of 3 over the 2. Square root of 3. Okay, well, let's look at this triangle then. The one he gave me in the picture. And here's my 60. Sine of 60 is still opposite over hypotenuse, square root of 3. Did I do that right? Oh, no, it was square root of 3 over 2. What happened? So notice you didn't help me. Cosine of 60 using this triangle is adjacent, that's 1/2 over hypotenuse 1. And this was square root of 3 over 2 over 1, by the way. And this is 1/2 over 1. You see, you get the same answers? You get the 1/2 and you get the square root of 3 over 2, the same as I got over here. 1/2 and the square root of 3 over 2. I get the same answers. But because he's on this circle, it makes it more complicated. What I guess the moral of the story is, you know the radius is always a 1 here, but you don't have to stay on this circle. You can just go to the regular 30, 60, 90 and do it from there. Or you can do it from a 45, 45, 90, 45, 45, 90. And you're going to get the same answers. You just got to remember 1, 2, square root of 3, 1, 1, square root of 2. You'll get the same answers, but you'll have to pay attention to one thing. What quadrant am I in? Okay, because all functions are positive here. So sine, but I'm not going to do no more. This is the only one I'm going to do, okay, by doing all that work. I'm going to look at my circle. Well, so my circle said sine was square root of 3 over 2. And cosine was 1/2. Just using that circle. Yes, I could do all the work, and I did all the work. I did it twice. I did it with this triangle, I did it with this triangle. Same thing. So using my chart, let's talk about, he's taking pi and he's subtracting pi over 3. Okay, how does that look? Here's pi. Here's pi. And I'm subtracting 60 degrees. So this was, where would be 60 at? It'd be the symmetry to this thing here. Look at here. It'd be here. If that's 60, that's 60. You see what I'm saying? So I'm going to draw it here. That's the angle he's talking about. Pi subtract pi over 3. Question is, what quadrant am I in now? Well, he wants me to say what is pi minus pi over 3? We'll do the math. 3 pi over 3 minus pi over 3 is 2 pi over 3. Or you could have said 90 minus 60 is, wait, did I do it right? 90 minus 30, that's what he's doing. No, he did minus 60. I just can't see it. What is 90 minus 60? Nobody? I can sit here all day. 90 minus 60. I'll just time. I'm timing to see how long it takes for someone to.
Oh, do you just want us to subtract that?
Yeah, 90 minus 60. What is that?
30.
Okay. If you're following along in the PowerPoint, he didn't put pi over 6 here. He did not put pi over 6 because that 30, my friends, that 30, he's talking about this angle here. That's a reference angle. We really are talking about the big angle, which is actually 2 of the 60s. If that's 30, then what's left? What's left out of? I messed up anyway. No, maybe you know what? I know why you guys are confused. I messed you up. I take back what I said. Actually, I probably should say, no wonder you're staring at me like that. But nobody said anything.
Isn't it?
Yeah, tell me, because nobody said nothing.
180 minus
Thank you.
60, isn't it?
Yes. Were you thinking that before?
Huh?
Were you thinking that before?
Yeah, that's why I was like, why 90?
Well, yell at me.
It's because I just thought you were doing something.
You know, I fell on my head. You didn't hear me fall, but I fell and I had suffered some brain damage right now, right before I was doing this problem. All right, so what is he going to put up there? What is 180 minus 60?
120.
120. That's 2 of 60s, right? That's 2 pi over 3. Thank you. That's got us all right. That's your voice?
Yes.
Thank you. What quadrant am I in if I'm doing the 2 of the 60s? When I drew my picture, I realized that can't be 30. Something's wrong. I had to go back and look at, oh my gosh. What quadrant am I in?
2.
2. Now look at the 2 pictures I have. Look at the red when it was 60. Now look at the when it's 120. What symmetry do you see? Over which? Do you see symmetry of the red? There's no reflection?
Yes, over the reflection over the y-axis.
Yeah, it is. Y-axis. Yeah, very good. And we're going to save ourselves the work. What's the ordered pair I'm at? Should be the opposite of the x, but keep the y. You see, opposite of x, opposite of a, keep the y because it's reflected over the y. So it's the same answer as the top, except it's opposite of the x, negative half. The y stayed the same. So the cosine must be negative half, and the sine must be the same. Not going to do all the triangle work. All right, now, thank you for helping me. Let me erase that second set of work. Okay, we're at pi plus pi over 3, which in English, if I was like speaking Spanish, I would say that's 180 plus 60. How much is that?
240.
That's 240, which is 4 of the 60s. So watch this. It's 4 of the 60s. It's 4 pi over 3, because pi over 3 is a 60, but 9 over 3 reduces to, I think, 4. Did I do the math wrong? Let me do it with common denominators, because I may have. That's going to be 3 pi over 3. Do that. 3. Let me erase it. 3 pi over 3 plus a pi over 3. Somebody, quickly, before I write it down, 3 pi over 3 plus a pi over 3.
4 pi over 3.
4 pi over 3. Yes. That means there's 240 degrees, so I am going to be down 1 pi over 3, 2 pi over 3, 3 pi over 3, and 4 pi. No, what did you say? How much? 4 pi over 3? Down here? Is that what you told me? 4 pi over 3? Yes, you did. So now what symmetry do I have with those two rays? Oh, well, first, what quadrant am I in?
3.
3. Okay. Symmetry? Hint, hint, hint. I push this one real hard. I rotate it till it lines up 180 degrees later. What symmetry is that?
Origin.
Origin. And what ordered pair am I at? Remember the rule for symmetry on the origin? We flip the x and the y. So it's the same answer I had up here, but they're both flipped. -1/2, comma, negative square root of 3 over 2. Think about it. The x value is negative, the y value is negative. That makes sense, okay? And I don't know why he's having us do this. I've never really cared about this particular idea comparing with pi over 3, but it talks about symmetry, so it's a good idea. But I don't have time for everything. Cosine would have been the -1/2, and the sine would be a negative square root of 3 over 2. Last one, I bet you any money, I don't even know. I bet he's taking us into quadrant 4 just for fun, okay? But let me erase the work that I have on that second set. Still keep that 60-degree angle over there, or pi over 3. And what is he saying? I'm at 2 pi minus 60. That's 360 minus 60. Or you can write it in terms of the denominator is 3. Multiplied by 3 over 3. That's 6 pi over 3 minus pi over 3. How much is 6 pi over 3 minus 5 pi over 3? 5 pi. If I keep waiting for you guys, we'll never get done. 5 pi over 3. What happened? I'm on that full circle all the way around. 2 pi. Take away the 60 degrees. So I should be, if I take away 60, that was, we said it was going to be 5 pi over, what did we say it was going to be? 5. No, we said it was going to be, yeah, 5 pi over 3. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, right here. There it is. Oh, missed it. Or 360, take away 60. Take away 60. So what symmetry is now with this ray and that ray?
Reflection over the x-axis?
X-axis. Quadrant 4, I predicted it. And when I flip over the x-axis, the x stays the same, 1/2, but the y becomes negative based on the rules that we already knew. I know you didn't remember all that. Who does? And the cosine is still a half, but the sine is now -3/2. Here's where he replaced the cosine of s equals x and the sine of s equals the y into the Pythagorean identity and called it sine squared plus cosine squared is 1. Okay, back to the idea of domain. Back to the idea of domain. S stands for kind of like your theta. Your domain is if you were to graph the sine curve, how far can I graph sine? I can go forever. I can go forever. But he only wants me, well, he did say he took the whole thing. How far can I graph it? Forever. Tangent and secant's a little different. So I hate taking the time to do this, but I want you to see it in the calculator. I may or may not get done with all of this today. Okay. Make sure now you go into radians because we are talking about the unit circle and we're talking about in the radian mode. So in mode, instead of degrees, which I see my degrees was on because day before yesterday we were doing degrees, but this chapter we're doing radians. So I'm going to radians. You have to do that too, guys. So now when I go to y equals and I decide to just graph sine just for fun, to show you what I was saying is true, graph it, and I got too much there, so let me shrink it. Oh, there it is. Oh yeah, beautiful. And if I do cosine with it, you're going to see the same thing. You're going to see, but it's going to be shifted. It's going to be shifted because remember what we talked about before, that I've told you that the sine starts at 0, 0, but the cosine starts at 0, 1. If I go up to the cosine, let's see, switch, there you go. Look at that ordered pair, 0, 1. They're the same picture, they're just shifted, okay? And they do go forever and ever and ever, okay? So let me go and do tangent. I'm going to turn these two off. Well, no, let me leave the sign on. I want to see what it looks like. Tangent. Tangent of x. And hit graph. Look what tangent does. Tangent goes forever also, but one little difference. Tangent does go on and on and on. But look what it's doing compared to the, I wonder why it didn't give me a different color. Let me change the color. Yeah, let me do yellow. Oh yeah, that's gonna look good. Not really, looks too close to green. So if I go back to where sine was, the original 0, let's see if I can find it. I don't think I can find it. Oh, I know how to do it. Zoom trig. It goes back to normal. Okay, so here's my sine curve, right? 0, 0. They both go through 0, 0. But look what the tangent did. They both go through 0, 0. Let me go back to this curve here. Come on, go with this one. But it goes down forever. Remember we talked about the asymptotes? And then it goes up forever. Look where the asymptote is. I'm going to run on the sine curve so you can see it. Go to the sine curve. Come on. Be my best friend. There it is. I'm on the sine curve. Look where the asymptote is. There it is. Oh. Stay there. Look what the x value is. What's it say? Somebody tell me. You're convincing me as a class that I should just do a fast video recording and just not do it live. Because I can't get through this if I'm waiting for you guys to act like you're there. All I asked you is tell me, looking at the screen, are you not seeing this on your are you seeing my calculator?
Yes, sir.
Okay. So if you weren't, I was like, what in the heck? You made me do all that work? What is the x value right now? It's in my top left-hand corner.
1/2 pi.
What's another name for 0.5? A half. Half of pi. Pi over 2. 90 degrees. Every 90 degrees, I have an asymptote for my tangent. Every 90, there is, well, you can't, he's got it in decimal here. You don't see it. The x value is the decimal because we can't read the number because it's half a pi. Half a pi was 1.5 something. I think, I can't see it. Let me zoom in. It does say half a pi. Never mind. It says half a pi. And then if I go to keep going and move it to the next asymptote. Let's see, am I there yet? Yeah, that's it, right? It's at the bottom here. That is 1.5 pi because it had to move a whole pi to get to the other asymptote. This distance here is a pi difference. My point is this: if we start at 0, it's multiples of pi. 1 pi over 2, 3 pi, was it 3 pi over 2? Is that what it said? Yes, 3 pi over 2 because 1.5 means 3 halves. 1 pi over 2, 3 pi over 2, 5 pi over 2. If I continue, come on, move over. Another asymptote, that should be 5 pi over 2. 5 over 2 is 2.5. That's what it says. So let me do the secant. Go out of there. I'm going to get rid of the tangent. And I'm going to put secant. I don't have a secant button. Is that what he wants in my notes? I don't remember what the note had. Was he doing a tangent? That was tangent and secant together, I think. So you'll see it's something very similar. Let me do secant. I don't have a secant button. 1 divided by cosine is secant. So now I'm graphing those two. Check it out. The asymptotes, are they in the same place? Are the asymptotes in the same place? You brought me a present.
Yes, I did.
Whoa.
There you go.
That's nice.
You're
Pretty.
welcome.
We're just getting loaded on this Med High stuff, right?
Yeah, we are. Be more next year.
Oh my, it's nice. Thank you. Are the asymptotes in the same place? Let me see. I'll go to the sine curve because I can trace that to the asymptote. Okay, I got to scoot over, I guess, don't I? Let me scoot. Well, let me scoot over because I'm tracing. Get off of that. I don't know if it'll let me. I can't move over. Won't let me go. I can't get it more. Oh, there it goes. He's got to pinch it right. All right. It shrunk a little bit, but this asymptote, where is it? 1.6. It's all in decimal now. That's not helping. What is 1.6? What does that look like, a number that we may have used? I'm not really on it. Sorry, I'm not really at the one. Let me make it red. There it is. Oh, there it is. 1. Shoot, too small. There it is. 1.57. What does that look like? 1.5. That's half a pi. Pi over 2 again. Next asymptote. Oh, come on. There it is. It just moves. It's so. 4.7. I don't know what that is. Could someone do, let's try it out. We already did pi over 2. Let's do the 3 pi over 2. No, that was 1. Try that. Somebody type in 1.5 times pi. Is that it? No
Yes,
one's
sir.
Okay, so I don't know why for now he doesn't want to do it in exact. He had it exact before. I don't know why. Maybe because the way I'm zoomed. No, it's not changing it. Anyway, so if you notice, I'm going to do one more just because. Instead of secant, let's look at a cotangent. Let's do, I did tangent already. No, I didn't. I did tangent. Let's do cotangent. That's 1 divided by tangent. If you're not doing this with me, you're just a spectator. I don't know why you're even here. You can just wait for the movie to come out. Mark you absent. Oh, wow. It looks like the tangent. One difference, it flipped. Tangent went from bottom left up to the top. This one is going from the top down to the bottom. And if I could find, if I go zoom trig again, so I can get it to be in the same place. Zoom trig. Okay, look at that. See how it flipped the pink lines, the pink curve? But I think you'd be surprised to find, I don't know why this time it didn't even show me my asymptotes. Yeah, I can't even, it didn't show me the asymptotes in this one. I don't know, must be having trouble because it's just not normal. But there's an asymptote roughly X value right here, roughly in there. I can see my red dot. I don't know what 0.84. Oh, there it is. It's got a pi in there. 0.834. I don't know what that is, that number. Could be, I'd have to try to figure out what that was. Not labeled, that's why he's having trouble. It's around there, whatever this, oh, here it is. That might be a good spot. What does that give me? That's better. Pi. Pi. What does this have to do with what he's asking? He's telling you that your domain for sine and cosine went everything. But obviously your tangent had multiples of pi over 2. Remember, we had 1 pi over 2, then we had 3 pi over 2, then we had 5 pi over 2. And then same thing for the secant, was exactly the same asymptotes. You're just starting out at, he says, start with n. N is 0. If n is 0, 2 times 0 is 0, 0 plus 1 is 1, 1 times pi over 2, there it is. If n was 2, 2 times 2 is 4, 4 plus 1 is 5 pi over 2. It jumped all the way to 5 pi to get the whole domain. That whole graph from left to right was in that little boundary. I don't want to play with that anymore. And I'm almost at the end of my time, so I did not finish. We can finish this last thing here. Find the exact values. Well, I cheated. I put the picture here. I put the picture here in case you don't want it. I didn't put it for you. I put it for me. I forgot. I didn't look at it close before. And I said, hey, that picture would really help me do these answers, but I don't need to. Really, let's be honest. 1 pi over 2, 2 pi over 2, 3 pi over 2, I am there. Okay, that ordered pair is 0, -1. What's the sine? Right here, 0. What's the cosine? I'm sorry, sine is there. Cosine is here. Sine is -1. Cosine is 0. Tangent is y over x. That's this answer over that answer. That's -1 over 0. It is going to be undefined, isn't it? Let's look over here. Well, he doesn't give me all the functions. It is 0, -1. And sine over cosine, -1 over 0 is undefined. So that would be undefined. You can do the same thing. I got 2 minutes. Let's do cosine of 7 pi over 4. Here's what I do. I know pi over 4 cuts that in half, cuts that 90 degrees, cuts that in half. That's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. I need one more. 5 pi over 4. That means this angle is a pi over 4. It's a 45 degrees. So here's what I do. I just make my triangle 45 because the reference angle is 45 degrees, pi over 4. 1 square root of 2. The sine or the cosine has to be 1 over the square root of 2, which is square root of 2 over 2. So is the sine. 1 over square root of 2 is still square root of 2 over 2. But be careful. Is cosine positive or negative in quadrant 3? Somebody. Can't believe it, guys. Nobody's really.
Positive.
Cosine? In this quadrant? Aren't the x's negative? All students take. Only tangent's positive here in quadrant 3. Everything else is negative because the x is negative, so your cosine has to be negative. So it's negative square root of 2 over 2. The sine is down. It's also negative. So the sine is also negative square root of 2 over 2. The tangent, though, would be positive if that's what you were thinking. The tangent would have been negative over negative, and you'd be correct. All right, I'll pick up with that. There's still a lot left.